Hello everyone, and thank you for joining us on this Nordic Tech webinar. This webinar will be around 60 minutes, and we have time at the end of the webinar to answer your questions. Your questions are highly encouraged, and please use the Ask a Question function for that at the end of the webinar. It is at the top right of the sidebar. These questions are anonymous and will only be seen by us. The chat is not anonymous. The chat can be used to chat amongst you viewers, but it will not be used, or you should not use it to ask us questions. If you have unanswered questions after the webinar, you will always get help if you go to DevZone. There we have a team of engineers working to help you. And as always, a recording of this webinar will be available together with the presentation later this week. Many of you have probably seen our first introduction to Meta webinar. For the second, more technical webinar, two of our firmware engineers are going to talk to you about developing Meta products with the nRF Connect SDK. And with that, I give over to Lukasz and Damian. Please go ahead.
Hello everyone, my name is Łukasz Duda. I joined Nordic Semiconductor 7 years ago and have been worked around our Thread and 15.4 solutions. Currently, I'm leading our R&D team, responsible for Matter protocol.
Hi, my name is Damian Krulik. I joined Nordic last year, and since the first day here, I've been working on integrating Matter with nRF Connect SDK.
If you haven't seen our previous introduction webinar, I would recommend you to watch it as well. Our colleague Krzysztof Loska explains what is Matter and how it works from specification point of view. You will learn there as well what is Nordic's solution for Matter. In this webinar, we'll fully focus on development side of Matter with some hands-on. We'll start with a few slides showing our software architecture and dedicated tools for Matter. We'll also recap how Matter over Thread setup looks like. Then we'll jump into more practical aspects. First, we're going to show you how to start by setting up the development environment, as well as Matter embedded sample. Then we're going to create a custom data model and application from a dedicated template. Lastly, we'll show you how to control the Matter accessory from the mobile phone. And of course, after the presentation, we're going to have a Q&A session. So without further ado, let's start with key component of Matter, which is its protocol implementation. The code itself is available openly for everyone and is hosted on GitHub. Sometimes it is called Matter SDK. With this open source approach, everyone that develops a Matter device can use exactly the same code base. This is, of course, a very important element for rapid adoption, as well as market success. The stack development is ongoing, and it evolves to implement, of course, all the features from the specification. However, already it is very advanced. To name just a few features, we have a data and interaction models, which help to describe the various functionalities and actions that can be performed on the devices. We have also security foundations and device commissioning, which allows user to add a new device to existing network in a secure way. Also, since Matter is based on IPv6 and various IP-enabled transports, such as Thread, transport management and numerous of framing procedures are implemented as well. One of the interesting facts about Matter is that its specification and code were not entirely written from the scratch. A few companies from across the industry have been contributing already market-proven technologies, as well as best practices into this project. So just looking on the numbers, there were almost 100 contributors to the GitHub repository who made more than 4,700 commits. Matter project wants to create and deliver a deployable code, not just a technical specification. That is why we have a unique implementation-first approach, where we vet integrations in practice and ensure that code and related tools are ready to meet the quality and user experience expectations. Finally, next to the core functionalities, Matter repository also contains several reference examples, both for Matter devices and Matter controllers, which are supported on multiple transports, such as Thread, Wi-Fi, or Ethernet. As it was already presented on the previous webinar, our main solution for Matter is based on nRF Connect SDK. This SDK offers an extensible framework for building advanced Matter applications. I encourage you to check our other webinars where we describe the details of nRF Connect SDK, as well as Zephyr operating system on which our SDK is based. But purely in the context of Matter, we have, of course, integrated Matter protocol implementation into our SDK with additional dedicated applications and samples. In the current release of SDK, you will find reference applications for door lock, light bulb, light switch, or weather station, as well as template sample, which is useful to create your own custom device applications. Matter is built on several protocols developed and certified by external standardization bodies, such as Thread or Bluetooth Low Energy. And to make it easier for you to create a Matter product, we do pre-certifying or pre-qualifying network stacks. For example, when you decide to use precompiled Thread libraries, you can leverage Thread certification by inheritance. One of the key distinguishing features is protocol coexistence. For example, you can run both Thread and Bluetooth Low Energy at the same time, which not only fulfills Matter requirements, but also creates opportunity for adding features such as device firmware upgrade over Bluetooth Low Energy, which you can perform in the background while operating on a Matter network. Lastly, by using our SDK, you can leverage our security components, which boost cryptographic operations for Matter using our hardware accelerators, or MCU boot, which implements secure boot. You can also find support for range extenders, such as nRF 21540, which offers enhanced link robustness. Nordic devices for Matter, such as nRF 52840 or nRF 5340, come with inbuilt support for NFC, which can tremendously simplify the device onboarding process by replacing QR codes with what is called Touch 2 experience, which we will show later on. We deliver a complete solution for Matter. Apart from mentioned software development kit, we include a bunch of tools which support development, programming, and debugging Nordic Semiconductor's SoCs, as well as the Matter firmware. First of all, both supported SoCs come with hardware development kits with all hardware layouts and schematics included. They facilitate development of Matter products by exploiting all needed features of our SoCs. For example, both include NFC antenna or external flash memory for over-the-air upgrade. We do have also dedicated variants of DKs in the form of dongles or some that include our power amplifier nRF 21540. Our SDK comes with native support for Seger Embedded Studio and nRF Connect for VS Code extension, offering IDE, which simplifies the embedded development, especially since they integrate useful debugging tools to identify coding errors at various development stages. Since Matter operates on Thread, we offer a bunch of useful Thread tools, such as Thread Topology Monitor, that visualizes the current mesh topology. You can also run a sniffer device on our DKs, which helps to troubleshoot communication issues in Wireshark, both for Thread and for Bluetooth Low Energy. There are also a bunch of Matter tools, which we will present during this webinar. But just to mention, exclusively with nRF Connect SDK, we deliver precompiled versions of Matter controllers to make product development easier. Before we jump to practical workshops, I want to make sure that elements of Matter over Thread setup are well understood. So just a fast recap from the previous webinar. the typical Matter communication happens between what is called Matter controller and Matter device. Bluetooth low energy is only used for commissioning the device into the network. However, afterwards, the application data exchange happens only over thread using IPv6. Matter controller, of course, may have the thread radio, but it is possible that it doesn't, which is actually typical for controllers implemented, for example, as a mobile phone application or PC-based application. In such cases, we would need to add additional device, which is thread border router that connects thread network to other IP-based networks, such as Wi-Fi or Ethernet, to which our controller is connected. For Matter, such device can be a generic thread border router that supports a service registration protocol. Finally, typically you don't want to create dedicated access point on a thread border router or a Matter controller, creating yet another Wi-Fi network, as it is much more convenient just to join to your home network. And this is the actual development setup that will be shown by Damian, where he will explain step by step how to create it. Bear in mind that this is one of the possible and maybe the most common setup. However, you may think of collapsed cases where a controller, thread border router, and Wi-Fi router are all in the same device. Okay, Damian, stage is yours.
Thank you, Łukasz. In this section, I'm going to show you how to get started with Matter using nRF Connect SDK. In the next section, that will start in about 15 minutes, I will demonstrate how to begin developing your own Matter accessory based on Nordic SoCs. I'll be using a thread device as a Matter device, so I will need to create the following network topology in the next couple of minutes. I'll be assuming that you have a Wi-Fi router up and running. It can be nearly any home router supporting IPv6. As for the Matter device, I will be using an nRF 52840 development kit with a Matter lock firmware programmed. The Matter lock is a ready sample in the nRF Connect SDK, so no coding will be required at this moment yet. Thread border router will be formed out of a Raspberry Pi 4, an nRF 52840 dongle, and Open Thread border router software. The dongle will be used as an Open Thread radio coprocessor, as the Raspberry Pi doesn't come with a built-in thread radio. Finally, I'll be using a laptop with Ubuntu 21 as both my workstation and a Matter controller. The controller functions will be provided by the Python chip controller available in the main chip repository. There's a couple more things which are necessary to replicate all the steps presented in this webinar. First of all, you need to have nRF Connect SDK 1.7 installed on your PC. If you don't, check the official nRF Connect SDK guide for instructions. You will also need Visual Studio Code with nRF Connect extension pack released by Nordic Semiconductor just a few weeks ago. Apart from that, your PC must be equipped with a Bluetooth LE adapter. It can be a BLE adapter embedded in your laptop, but in case you don't have one, you can use the HCI USB sample in the nRF Connect SDK to turn a spare nRF 52840DK into a BLE adapter. Last but not least, you will need a microSD card reader and the ARPA imager tool to install an operating system for the Raspberry Pi. Here are some of the hardware components that I will be using throughout the video. The nRF 52840DK will become a Matter lock device. The Raspberry Pi 4 and the dongle will be used to create a thread border router. Note that the Raspberry Pi is connected to my home router using the Ethernet cable. Let's begin with programming a Matter lock sample onto the nRF 52840DK. First, I'm opening my nRF Connect SDK installation directory in Visual Studio Code. Then I'm clicking the nRF Connect icon on the left, which opens a panel that allows me to add an application to the list of active applications managed by the extension. In order to do that, I'm clicking the Add Application button and choosing the Matter log sample. The next step is adding a new build configuration for the sample. I am making sure that the selected board is nRF 52840DK and clicking the Generate Config button. It starts the build process automatically. After the firmware is built, a new build directory either shows up automatically in the list over here, or you need to use the refresh button. At this point, I can program the firmware onto the development kit using the erase and flash to board action. Finally, I am ready to open a serial terminal with the development kit device node name as an argument and reset the board to get access to the application logs and verify that the device boots up successfully. Now that the Matter device is ready, let's focus on creating a thread border router out of the Raspberry Pi and the nRF 52840 dongle. As was mentioned before, the dongle will work as an open thread radio coprocessor, so it must be running an appropriate RCP firmware. To that end, I am opening a new terminal and searching for the coprocessor sample from the nRF Connect SDK. I am using the following command to build the RCP firmware for the nRF 52840 dongle. Note that I need to add 3 configuration overlays to enable OpenThread radio coprocessor library, thread 1.2, and a USB transport for the radio coprocessor. Flashing a firmware onto the nRF 52840 dongle is a bit different than it was in the case of the nRF 52840DK, since the dongle doesn't contain the J-Link programmer. Instead, the dongle contains an immutable bootloader which can be used for the firmware upgrade, but that requires a special firmware image format. In order to convert the image to the supported format, I need to install the nRF util package using Python pip. Then I'm using the following command to do the conversion. Now I am plugging the dongle in a USB port of my computer and I'm pressing the reset button on the dongle to reboot it to the bootloader. The red LED should start blinking. Finally, the firmware image can be upgraded using the following command. In the last parameter, I need to specify the dongle device. Once the operation is completed, I can plug the dongle in a USB port of the Raspberry Pi. Now let's set up OpenThread border router on the Raspberry Pi. I am inserting the microSD card of the Raspberry Pi into my computer and running the RPi imager tool. Now I am selecting the Raspbian OS and the proper SD card and starting the installation process. It may take a while, so I'll take a break and see you when it's done. Okay, the installation is done, but I also need to enable the SSH server on the Raspberry Pi. It can be done by creating an empty SSH file on the boot partition of the SD card. It is also a good moment to enable router advertisements on the Linux machine, so that it is able to automatically configure routing to devices in the thread network. It works in such a way that the OTBR sends unsolicited router advertisements informing that IPv6 addresses starting with the thread network's ONOMESH prefix should be routed via the OTBR. Unfortunately, router advertisements are by default ignored on many popular Linux distributions, such as Ubuntu, so I need to change the following system settings. Note that those settings must be reapplied after the system reboot. Now I can move the SD card back to my Raspberry Pi and boot the device. Once the device has booted, it advertises itself over DNS-SD, so I can use the following command to SSH to the device. In order to build and run OpenThread border router, I need to complete the following steps. First, I'm cloning the OTBR repository. Then I'm checking out the commit compatible with nRF Connect SDK 1.7. The commit ID can be found in the nRF Connect documentation. Then I'm running the bootstrap script to install all necessary dependencies. Then I am running the setup script using the following command. The infra-if name variable should contain the interface through which the device is connected to the home router, as it will be the interface used for sending the aforementioned router advertisements. After the setup, I need to modify the OTBR settings to make it work properly with the RCP device. In order to do that, I am copying the symlink name of the RCP device. It is important that it be symlink, not the device node name itself. And then I am pasting it in the OTBR agent configuration file. Additionally, I'm adding uart-reset parameter. I am saving the file and restarting the OTBR agent service as well as the OTBR web service. If everything has gone well so far, entering the IP address of the Raspberry Pi in a web browser should open the OTBR web interface. I am using the web interface to form a thread network. I've set up the Matter device and the border router, so the last piece is the Python chip controller. Precompiled packages of the Python controller are published by Nordic on GitHub, so I can open the following address, find SDK-connected home IP repository, navigate to the releases page, and download the chiptool Python Linux release zip file. The zip file contains two Python wheel packages for x64 and ARM64 architectures. I am unpacking the archive to a known location such as the home directory. After that, I am installing the wheel package for the x64 architecture with the following command. With all the components set up, I am ready to test the commissioning and controlling the Matterlog device with the Python controller. To that end, I am starting the Python controller. And now I'm pressing button 4 on the Matterlog device to enable BLE advertising. The application logs indicate that the BLE advertising has started. You can see two other important entries: the device discriminator and the pin code. This information can be used to establish a secure connection to the device over BLE with the following Python chip controller command. The last argument is the node ID to be assigned to the device. Now I could use the secure channel to send thread operational dataset to the device, but how do I know which operational dataset to send? The dataset can be exported from the border router, so let me switch the terminal to the one on which I am connected to the border router and run the following command. I am copying the output to the clipboard. And now let's go back to the Python controller and send the dataset using add thread network command from the network commissioning cluster. The command takes three positional parameters, such as node ID of the device, endpoint ID, and group ID, which doesn't really matter in this case. And there are also three special parameters. The first one is the operational dataset encoded in hex, the breadcrumb, and timeout. After sending the operational dataset, we can enable the thread network on the remote device using enable network command from the network commissioning cluster. It takes the same positional parameters, and the only different parameter is the network ID, which should be extended PAN ID. And now we can close BLE connection as we will no longer need it. The Matter log device is now ready to be controlled over the Matter network, but the Python chip controller doesn't know the IP address of the device. Therefore, I need to use the resolve command to resolve the node ID to its IP address using DNS service discovery. The first parameter is the fabric ID, which for now is hard-coded, but it will change in the next versions of Matter. Finally, I can unlock the door using the off command from the on-off cluster. Observe that the second LED on the device will change its state. Now that we've set up the testing environment, let's learn how to create a custom Matter device using the nRF Connect SDK. As an example, I will create a temperature sensor device which can be turned on and off. Here is a very simplistic view of a typical Matter application. Each Matter application must provide an integration layer with the Matter core components, the data model layer in the form of clusters which contain commands and attributes that are to be accessible over the Matter network, and on top of that all, the application logic such as turning on and off a light bulb in response to certain commands. The data model clusters can additionally be divided into utility clusters required just by the fact of being part of a Matter network, and those that are specific to a given application. The nRF Connect SDK contains a Matter template sample, which provides the parts presented as the colored boxes, so it can be used as a starting point in creating a custom Matter application. During this exercise, I will demonstrate how to create a temperature sensor device that can be turned on and off. To that end, I will enrich the template sample with temperature measurement and on-off clusters, and with the application logic that will periodically fetch the simulated temperature sensor and update the corresponding cluster attributes. I have used the term cluster in the previous slides without actually defining it. The cluster is a data model building block in Matter that represents a specific functionality such as turning on and off or measuring humidity. It can also be seen as a container for commands, attributes, and events, some of which are mandatory, some of which can be optional. Clusters are organized in containers called endpoints. Endpoint with ID 0 is reserved for Matter utility clusters that take part in the commissioning and management of the device. Endpoints 1, 2, 3, and so on can be used for application clusters. A single endpoint should provide functions of a single device type, so a complex device which combines functions of multiple device types should contain multiple application endpoints. Having gained all that knowledge, let's build a temperature sensor device. The nRF Connect for Visual Studio Code has a nice feature which allows you to create a new application based on any existing application. I will use that feature to turn the Matter template sample into the temperature sensor application. First, I am clicking the Open Welcome Page button and selecting the Create a New Application from Sample option. Then, I am selecting the freestanding type of application, which means the application which uses the pre-installed nRF Connect SDK. Then I'm entering the location and name of the application. And choosing the sample on which my new application should be based on. Then I'm generating the application. Now, the first thing I need to do is to modify the data model configuration of the application to add the temperature measurement and on-off clusters. The data model configuration is stored in template.zap file. A zap file is simply a JSON file which contains configuration of clusters, commands, and attributes enabled for a given application. I will not modify this file by hand because Chip provides a dedicated software called ZapTool to edit this kind of file. In order to run the ZapTool, I am opening a new terminal and moving to the nRF Connect SDK installation directory. Then I'm moving to the modules/lib/matter directory. And from here, I'm running the following script. The script takes a single argument, that is a relative path to the zap file. And this is what the application looks like. As you can see, it presents all available clusters, but you can also make it display only the enabled clusters. There's currently only one endpoint, the endpoint 0. Let's add another one for the application clusters. Note that in the screen you can choose a desired device type. I'm choosing the temperature sensor device type. There are a few clusters added to the endpoint by default. I am removing the first two as I don't need them, but I do need the on-off cluster. Also, I am clicking the configuration icon to further configure the cluster, as by default it doesn't have any commands enabled, and I need at least on and off commands. After making the changes, the ZAP configuration looks as follows. The ZAP configuration is not used directly by Matter applications. Instead, it is used to generate the source file for handling given clusters. To regenerate the code after making the changes, I need to run another script. After adding the new clusters, I need to do certain changes in the source code of the application to make it interact with the newly added clusters. The heart and the main loop of the application is based on an event queue. There are currently 3 types of events, all involved in the factory reset functionality. To model the sensor behavior, I need 3 more. First, I need 2 event types for activating and deactivating the sensor, and 1 more for triggering the sensor data update. As you may recall, the sensor once enabled should update the measured value periodically, and for that purpose a timer is needed. The application already contains a timer, so I need to add another one. The timer must be initialized in the init method of the apptask class. It can be initialized using kTimerInit function from the Zephyr, which takes 3 parameters. The first is a pointer to the timer object. The second is a function to be called when the timer expires. And I want that function to just create and post the sensor fetch event. And the third parameter is the function which is called when the timer is stopped, and it can also be a null pointer if it's not needed. After adding the timer, I need to modify the dispatch event method used to process subsequent events from the main queue. I'm extending the existing switch case instruction to support newly added event types as well. When it comes to handling the sensor activate event type, I wanted to start the sensor timer, because the sensor timer will cause periodic updates of the sensor data. The timer can be started with kTimerStart function from Zephyr, and it takes 3 parameters. The first one is a pointer to the timer object. The second is the amount of time after which the timer expires for the first time. And the third parameter controls how frequently the timer expires after the first invocation. The sensor deactivate event type should be handled the opposite way, so by stopping the timer. The sensor fetch event type is more tricky because the development kit doesn't contain a physical sensor, so I must somehow simulate the sensor. I will use a simple variable for that. The variable will be initialized with 0 and incremented each time the sensor is updated. And I'm also making sure that the value wraps around when it goes to 20. Now, what do I do with this value? I want to put it in the temperature measurement cluster, in the measured value attribute of that cluster, and to do that, I need to include another header file, which contains a helper function to do that. After adding the header file, I can use Ember AF temperature measurement cluster set measured value callback function, which takes 2 parameters, the endpoint ID and the temperature measured in 1/100ths of Celsius degrees, so I must multiply my variable by 100. The code changes for updating the temperature sensor are done, but there's currently no one to enable the sensor. I want the sensor to be controlled using the ONOFF cluster, so I need to add a callback function that will be called whenever the ONOFF attribute from the ONOFF cluster is changed. To implement such a callback, I must include 2 more header files. Then I can write the callback, but it has a rather complex signature, so let me copy-paste it from other samples. Now, what should the function body contain? First, the callback will actually be called if any attribute from any cluster is modified, and I'm only interested in the ONOFF cluster, so let me filter out other events. Then I'm adding the code posting an event. If the current value of the attribute is non-zero, post the sensor activate event. Otherwise, post the sensor deactivate event. And that's all code changes that are necessary, but I also must modify the cmakelist.txt file, as currently the cluster source files are not included automatically based on the ZAP configuration. First, I'm adding the on-off cluster source file, and then the temperature measurement cluster source file. And that should be it. Let's try to build and flash the sample in the same way as the log sample before. Then I'm running the previously presented commands to commission the device onto the network. The only difference is that this time I'm using the node ID 2 instead of 1. And we are ready to test the device. First, I'm sending the on command to enable the sensor. Then I'm reading the measured value attribute from the temperature measurement cluster. As you can see, it's equal to 15 degrees. And if I read it again after a few seconds, it's equal to 3 degrees. So it works as expected so far. Now I'm turning the sensor off and read the temperature twice. As you can see, now the measured value does not change, so the sensor is deactivated.
Thank you, Damian. At the end, I would like to quickly present you how to interact with Matter devices using mobile phone. For this to happen, I will generally use the same setup as Damian, though instead of using PC-based Python chip controller, I will use dedicated Android controller application. On the accessory side, instead of using a door lock sample, I'm going to program the light bulb application on our dual-core nRF5340 SoC. Android chip tool application is part of Matter SDK effort. It supports Matter commissioning over Bluetooth Low Energy and application data exchange over IP. You can obtain devices onboarding information such as discriminator or setup pin code, both from QR code or from NFC tag of the accessory. The application itself supports few device types presented on the slide, which generally covers functionality of all samples delivered in the nRF Connect SDK. Specifically, dimmable light bulb that I will focus on right now. Let's start with building Matter light bulb application. For that, click on Add Application button and navigate to the Matter light bulb sample location. Now we have to generate configuration for nRF53 development kit and of course build the sample itself. Note that despite nRF53's more advanced SoC with 2 cores, development of Matter device application is very similar to what you have seen with nRF52. This is due to all implemented low-level abstractions. Right now, we are building 2 images. One for the network core, containing a BLE controller, 15.4 radio driver for Thread, as well as multi-protocol service layer. The second image is for application core, and it includes Matter protocol implementation, thread stack, BLE host, and of course, custom application logic. Since the example is built now, let's choose Erase and Flash button to load the firmware into the device. At the same time, we can open serial connection to this device to see its logs when device boots. On the right, you can see my Android phone screen. We have to first download the Android chiptool application from our GitHub repository. The link to this web page is available in our documentation in the Matter Tools section. So let's choose correct architecture. Now let's install this application. Of course, we need to accept necessary permissions. As I mentioned, we can commission the device into the network using QR code or NFC tag. Let's start with the first option. The link to the QR code image with onboarding information can be found in the device's logs. So let's open this link. Now we can click on Provision Chip Device with Thread. We need to grant permission to the camera and capture the QR code. The commissioning process has been started automatically, and it happens over Bluetooth Low Energy. Let's leave default thread credentials. And with that, commissioning has been finalized. To control the light bulb over IP, let's just click on Light On-Off button. Now we have to discover IPv6 address of the node using DNS service discovery. And now let's try to change the state of the light bulb. We can turn it on. And we see that when we read the value, we see that it is set to true. We can also turn it off. And we see that the current value is set to false. We can also change the brightness level of the dimmable light bulb, which you can observe on the decase LED or on the device log. Now let's back and try commissioning the device using NFC. I'm pressing button 1 on the decay for 6 seconds to perform factory reset on the device. At the same time, let me close all the applications on my mobile phone. Now I'm tapping the phone to the NFC antenna of the nRF53 development kit. And as you see, Android automatically detected NFC tag and opened the right application. From now on, the behavior is exactly the same as was shown previously.